So this is the kind of thing you get. So so of course what you see. So let's look at it a little bit closely. We have this Fermi level, right? Fermi level. What is Fermi level? Well, this is the dividing line where you have all the few energy levels. So all the states are few. Okay. And then above the Fermi level, you have empty level or empty orbital. So this is kind of like HOMO and LUMO kind of concept. And so this is all these virtual state or empty state like this. Okay, so that's the typical electronic structure plotted in a way of density state. And now you put in this photon. You have h mu or h pi omega, depending on how you explain. So h mu is better. It's just the photon energy. It's about this y. Okay, so you can choose the energy quantity that you want. So depending on which light source that you use, you can have a discrete photon or finite energy. Each photon has the same energy like this. Okay, so you're looking at Western light source such as aluminum K alpha radiation, for example, aluminum K alpha radiation, which indicate that energy is about 1486 electron volt. So that's the width, the energy of one photon. So what happened in the photoelectric effect is that in the photoemission process, the photon, this must be added up to, so as you move this photon around, okay, so you would have, you think of this as a scan line that you're moving it across. You're scanning down into the field energy state. As you go down into the energy state, what you get is that you can excite. Okay, so you can excite this photon. So let's say I move this bar to this line, this deep line called here, right, like this. What do you get? What you can get is that you can first move this energy level, right, whatever electron you have in here, to the vacuum level, right? So that's you bring it to the to become a free electron. So this is the Spicer model excitation, and then transport. And then once you get the surface, you still have some energy left. You still have this much energy left, right? So if I go from here to here, you first excite the electron up to here, and then whatever out here, the electron will carry this amount of energy as kinetic energy. Okay, so this is the amount of kinetic energy you see here. Okay, so you can imagine if I move my photon bar across, I'm scanning all this. I'm exposing these field energy level, right? All this structure we expose down here as kinetic energy. So this is the binding energy, as you see from here to here. This is my photon energy. This is my binding energy up to so the binding energy up to my free energy level. Okay, and then what's left is my kinetic energy. So this is my kinetic energy. There is some confusion about how you measure this binding energy. And there's different reference points, because if you reference your binding energy, technically you should reference your binding energy in solid. When people talk about binding energy, they reference it to the Fermi level in here. But of course the Fermi level is not really free, because you have a little bit of extra energy before it actually becomes free electron, and this extra energy difference is known as the work function. Okay, so sometimes the difference between free atom and molecule and solid is that you don't have this work function in the case of free atom and molecule. In the case of solid, you have to consider this extra sort of differences in energy between the free vacuum level, so-called vacuum level, where the electron becomes free, and the Fermi level where every electron can fill up to that state. And this is work function. So in the modified for solid, for Einstein equation, you have the kinetic energy is measured from the vacuum level, of course. So from here to here, is just the photon energy minus the sum of the plus the binding energy, which is measured from the Fermi level. Okay, so this bit plus this bit is what is left behind after you take out the kinetic energy from here. Okay, so in other words, what I'm saying is it's really just the Einstein equation is really nothing more than a conservation of energy, because your photon energy must be split into the part whereby you bring the electron from the field state to the vacuum level, which require energy of EV, the binding energy, plus the work function. And then what is the rest will be exhibited as the kinetic energy right here. Okay, so so it's quite easy to understand in terms of the Einstein equation like this. And the work function normally is about 4 to 5 electron volt. So this difference here is normally substantial because you may get it wrong if you don't use it properly. If you do not count into the work function like this. Okay, so that's one thing about the Einstein equation in the case of emission. And then there's other thing. So here we are looking at Einstein equation. If you consider energy conservation, we would have basically Einstein equation is before and after the photon absorption of the photon. So this is final state and initial state should equal to the photon, right? So we consider energy conservation of the electron in the solid and monitor this energy of the electron before and after. You would get this, right? And so conservation, so there's more than meet the eye. It could be a very complicated process. We're just looking at just the energy consideration so far. We haven't looked at any directional consideration, angular consideration of this emission of this photon. So we take a look at this. How, this different direction, you look at different direction from the surface, the intensity of your electron changes depending on how you look, where you look. And this directional effect must depend on the electronic band structure inside, because it must depend on how your atom are arranged inside your lattice. Okay? So here you look at conservation of momentum of the electron before and after. So this is basically conservation of momentum, the sum of the two electron before and after. It looks like a difference here, but it actually is a sum because the direction, right? The difference in the momentum must equal to the photon, the momentum of the photon, and the momentum, linear momentum of the photon, of course, is 0 in the case of photon. Photon does have an angular momentum of 1. This is why in the case of dipole transition, when you change the angular momentum in the case of spectroscopy absorption, you always have this selection rule of delta L plus or minus 1. And the reason is because photon has an angular momentum of 1. Okay? Whereas photon has no angular momentum, no linear momentum. So in the case of linear momentum, this should be approximated to 0. So you should have before and after. In the case of the electron, they should be equal to one another. So what does that mean when you say that the linear momentum is before the absorption of photon and after the absorption of photon is the same? What that means is that you can only have vertical transition is allowed in the band. Okay, so this is why you cannot really have for direct transition. You gotta find somewhere. There's gotta be a energy state up in that matches the energy difference that you have before you can have the absorption of photon. If there's no upper state that matches the difference between that state and the ground state, you would not have absorption of photon. Okay, so that's the power of Einstein's idea, is that you gotta have discrete, so-called resonant transition between one state to another. You cannot have a continuum transition. And this is what quantum mechanics gives us, of this discrete or quantum idea of absorption, of transition from the ground state to the excited state. In Newtonian way of thinking, of course, any absorption is possible. There's no discrete state in your electronic structure.